Introduction. Far beyond the shimmering veil of Earth's skies lies a drama unlike any other unfolding mystery that may one day reshape the solar system as we know it. This is not the tale of Earth, nor even of our sun. Instead, it is the story of a cosmic giant, Jupiter, the planet so massive it could hold over 1,300 Earths, and whose gravitational reach has silently sculpted the destinies of planets, moons, and comets for billions of years. But what if this titan, so seemingly immovable in its celestial throne, were to become the target of an unimaginable cosmic event? What if Jupiter's stability were disrupted not from within, but from a distant star or rogue, wandering light inching its way across the galaxy? Could an interstellar encounter with our nearest stellar neighbor, Proxima Centauri, one day send ripples through our planetary system, altering the fate of Jupiter and perhaps everything else? Throughout this audiobook's journey, we'll venture into both known science and speculative frontiers. We'll explore how stars move through the galaxy, what gravitational disturbances they can cause, and what fate might await Jupiter in scenarios where Proxima Centauri, another stellar visitor, crosses paths with our solar family. From orbital mechanics and gravitational waves to the possible fragmentation of gas giants and ejection from the solar system, each chapter will open a new door into this wild cosmic hypothesis. This is not merely science fiction, it is an examination of plausible futures and the delicate gravitational dance that holds everything together. So, find a quiet space. Let your imagination drift across the interstellar void and prepare to explore the incredible, bizarre, and perhaps even possible fate of Jupiter should Proxima Centauri come too close. Chapter 1. The Galactic Ballet. How stars wander through the cosmos on a human timescale. The night sky appears eternal and unchanging. The stars seem fixed, quietly glowing in their positions as though pinned to a celestial canvas. But in reality, the universe is alive with motion. The stars are dancers in a vast and ancient ballet, each one tracing its own intricate path through the galaxy. This is the backdrop to our story, a galaxy in motion, where nothing stays in one place forever. Every star in the Milky Way, including our sun, is in orbit around a galactic center. These orbits are not perfect circles, but elongated ellipses, slightly tilted and ever shifting due to gravitational nudges from other stars. Dark matter and massive structures like spiral arms. Our sun, for instance, completes one orbit around the Milky Way's core every 225 to 250 million years. That's what we call a galactic year, and Earth has only made about 20 of them since its formation. As the sun moves, so too does every other star in the galaxy, each at its own speed and on its own trajectory. Sometimes these paths come surprisingly close to one another. Not often in terms of daily experience, but often enough, given the scale of cosmic time. Over billions of stars, even at distances of a few light-years, their mutual gravity can shift the orbits of comets, distort outer planetary disks, and, in extreme cases, destabilize the orbits of planets themselves. Though such encounters are rare on human timescales, they are not uncommon over cosmic ones. Astronomers have found evidence of these interactions in other star systems. Some stars show warped debris disks suggesting gravitational disruption. Others have rogue planets' worlds ejected from their home systems by massive gravitational disturbances. These rogue planets now drift through the galaxy alone, cold and unbound to any star. Some may have once orbited giant planets like Jupiter before their systems were torn apart by passing stellar giants. And here, in this grand ballet, enters Proxima Centauri, the closest known star to our Sun, just over 4 light-years away. It is part of the Alpha Centauri system and orbits the 2 larger stars in a slow, sweeping ellipse. While Proxima is smaller red dwarf, barely an eighth the mass of the Sun-its proximity and eventual drift, may hold consequences far beyond its humble size. Over long stretches of time, even small motions accumulate. Astronomers model stellar motion using high-precision measurements of a star's velocity and direction. These calculations tell us that stars, including Proxima, are not locked in place. They move them. Sometimes they move toward us. But how likely is it for such a star to come close enough to affect our solar system? The answer lies in probability, trajectory, and time. Models predict that several stars have passed close to the solar system in its history, and more will do so in the distant future. One star, named Scholz's star, is thought to have passed within less than a light-year of the Sun some 70,000 years ago. That's practically next door in cosmic terms. A star passing within 1 light-year might not be close enough to disturb the inner planets. But if it ventures within 0.5 light-years, or worse, 0.1, the potential for disruption becomes very real. The Oort cloud, a vast spherical shell of icy objects that envelops the solar system, extends out to these distances. It is incredibly fragile. The slightest nudge from a nearby star could send comets raining toward the inner planets or jostle the orbits of gas giants like Neptune and even Jupiter. And so, the galactic ballet continues. The stars whirl and glide through the Milky Way. Like dancers on an endless stage, each influenced by the gravitational pull of others. Over eons, their steps bring them closer and farther, sometimes in perfect synchrony, and other times in near catastrophic proximity. Jupiter, the behemoth of our solar system, sits at the center of our tail. But to understand what may, one day, threaten it, we must first understand the cosmic ocean in which all these celestial bodies drift. In this dance of stars, even a seemingly distant step from a quiet neighbor like Proxima Centauri can send ripples that echo across entire systems. In the next chapter, we'll take a closer look at Proxima Centauri itself, what kind of star it is, how it moves, and what makes it a potential agent of change in the future of our solar system. The mystery deepens and the possibilities stretch beyond imagination. Chapter 2. Meet Proxima Centauri, our mysterious nearest neighbor, nestled in the southern constellation of Centaurus. Just over 4 light-years away lies the closest star to our solar system, Proxima Centauri. Faint red dwarf remained hidden from human awareness until 1915, when it was finally identified as part of the Alpha Centauri system. Yet its closeness is deceptive. Proxima Centauri is neither bright nor easily spotted. In fact, it is invisible to the unaided eye. But its small size belies the immense influence it could one day exert. Proxima Centauri is a red dwarf, the most common type of star in the Milky Way, with only about 12% the mass of the Sun and less than 15% of its diameter. Proxima is small, cool, and dim. If the Sun were scaled down to the size of a basketball, Proxima would be no bigger than a golf ball, and yet it burns on slowly and steadily, with an expected lifespan of trillions of years. Far outliving stars like our Sun. Red dwarfs like Proxima are fully convective, meaning their internal heat is constantly stirred and distributed. This prevents the buildup of helium in their cores and allows them to burn their hydrogen fuel far more efficiently. As a result, Proxima will outlive most of the stars in our galaxy. It is not a flashy star, but in cosmic terms, it is patient and enduring. Orbitally, Proxima Centauri is loosely bound to the Alpha Centauri A and B pair, forming a triple star system. It orbits these larger stars at a distance of roughly 13,000 astronomical units, so far that it takes hundreds of thousands of years to complete a single revolution. This vast distance also means that Proxima is somewhat free to drift, its gravitational leash tenuous at best, and drift it does. Astronomers have mapped the motion of Proxima Centauri with great precision. Using data from observatories like Gaia, we now know its radial velocity, its speed toward or away from us in proper motion. Its movement across the sky. Combining these gives us a three-dimensional picture of how this faint star moves through the galaxy and how it may eventually cross paths with our own system. Proxima is currently moving slightly away from us, but due to the gravitational interplay with Alpha Centauri A and B, its path is not linear. Over immense periods of time, perturbations from the galactic tide or passing stars could redirect it toward us. In some scenarios, Proxima might make a closer pass to the Sun, entering the outer reaches of the solar system. While such a visit might take millions or even billions of years to unfold in cosmic terms, it's not impossibly simply a matter of time. What makes Proxima particularly interesting is that it's not just a passive drifter. It is highly active for a red dwarf. Though small, it unleashes powerful stellar flare bursts of radiation hundreds of times more intense than any from our Sun. These flares are of great concern for any potential life on its known planet, Proxima b, a roughly Earth-sized world. In the star's habitable zone, yes, Proxima Centauri hosts exoplanets. In addition to Proxima b, which orbits very close, just 0.05 astronomical units away, there may be at least one more confirmed planet, Proxima c, and possibly a third unconfirmed body. These worlds, though intriguing, are constantly bombarded by radiation from their turbulent parent star. Any atmosphere on Proxima b may have been stripped away, and any life would need to be exceptionally hardy or hidden beneath the surface. But while Proxima's planetary system is fascinating in its own right, our attention is drawn to a more speculative yet plausible scenario. What happens if Proxima wanders too close to our solar system? Given its mass, even a distant flyby, say, within a light year or less could disrupt the Oort cloud. The gravitational disturbance might stir long dormant comets, altering their orbits and sending them toward the inner planets. With enough force, it could even jostle the outer planets Uranus, Neptune, and, critically, Jupiter. If Proxima Centauri were to pass even closer within 0.1 light-years, the consequences would be far more dramatic. Simulations suggest that such proximity could destabilize gas giant orbits, especially if combined with other stellar interactions. Jupiter, with its massive gravitational pull, might react violently, either shifting its own orbit or disturbing those of the planets and moons around it. It could even be ejected from the solar system altogether, cast adrift into the cold interstellar void. This is not idle speculation. Astronomers routinely model the gravitational effects of passing stars on planetary systems. Similar events may have occurred in our galaxy countless times. There is no law of physics preventing it, only the vastness of space and the patience of time. As we gaze up at the stars, it's tempting to imagine them as fixed points, like lanterns hung on a ceiling. But stars like Proxima Centauri remind us that the cosmos is in flux. The night sky is not a still painting, it's a living sea, where suns sail like ships, sometimes drawing near, sometimes fading away, always in motion. In the next chapter, we'll shift our gaze to Jupiter itself. We'll explore its immense power, its vital role in the solar system, and why this giant planet is both a protector and a potential point of catastrophic vulnerability. It will be Jupiter that stands on the front lines of this celestial collision. Chapter 3: Jupiter's Gravitational Empire. The solar system's silent architect. If the Sun is the heart of the solar system, then Jupiter is its shield, its governor, and perhaps even its architect. Towering in mass, cloaked in turbulent clouds, and girdled by swirling storms that have raged for centuries, Jupiter is not merely another planet in orbit. It is a colossal force, one that has shaped, defended, and redefined the architecture of our cosmic neighborhood since the very beginning. With a mass more than 300 times that of Earth, Jupiter holds over 70% of the planetary mass in the entire solar system. Its sheer size is staggering. If you combined all the other planets, asteroids, moons, and comets, they would still fall short of equaling Jupiter's mass. Its volume could engulf over 1,300 Earths, and yet it spins with stunning speed, completing one rotation in just under 10 hours, giving rise to intense winds and immense equatorial bulges. But beyond its physical grandeur, Jupiter exerts a more subtle and far-reaching influence: gravitational authority. Early in the formation of the solar system, it was Jupiter's presence that disrupted the growth of a planet between Mars and itself, scattering the material that would become the have formed at all. Even today, Jupiter plays a vital role as the solar system's cosmic bouncer. Its immense gravity captures or deflects incoming comets and asteroids. It's believed to have significantly reduced the frequency of catastrophic impacts on Earth by intercepting objects that might otherwise be drawn inward toward the Sun. This protective effect is not perfect. Earth still bears the scars of massive impacts, but without Jupiter, the threat would be far greater. But protection is only one part of the story. Jupiter also rules over a vast system of moons, more than 90 confirmed so far. Among them are some of the most fascinating worlds in the solar system. There is Io, a volcanic inferno spewing molten rock across its tortured surface. Europa, with its icy shell concealing a vast subsurface ocean that might harbor life. Ganymede, the largest moon in the solar system, even bigger than Mercury. And Callisto, ancient, cratered, and enigmatic. Each one dances around Jupiter in a gravitational choreography that is both delicate and powerful. These moons exist in constant tension, locked into resonant orbits that cause internal flexing and heating. Tidal forces generated by Jupiter's stretch and squeeze them, creating frictional heat that drives geological activity. Without Jupiter, these moons would be inert, frozen relics. With it, they become dynamic, living laboratories. Jupiter's gravitational field also subtly affects the orbits of the other planets. It helps stabilize the inner solar system to some degree, but can also induce small perturbations over time. In fact, long-term simulations show that the inner planets, including Earth, might experience orbital chaos over billions of years, largely due to gravitational nudges from Jupiter and Saturn. Jupiter's orbit is not perfectly circular. It is slightly eccentric, and it wobbles due to the pull of the other giant planets. These variations might seem minor, but in a tightly balanced system like ours, even small shifts can cascade into larger changes. It is this delicate gravitational interplay that keeps the planets aligned in their current configuration. Now, imagine introducing an external Força rogue star like Proxima Centaurian to this already complex equation. The addition of even a subtle gravitational pull from a passing star could displace Jupiter's orbit by a fraction of a percent. And yet, that tiny nudge could be enough to alter the timing of its gravitational influence, throwing its moons out of resonance, nudging comets onto dangerous paths, or disturbing the protective balance it provides Earth. Worse still, if Jupiter's orbit were perturbed enough, it could become a destabilizing agent itself, further migrating inward toward the inner planets or outward into a more erratic orbit. In extreme cases, Jupiter might be ejected entirely from the solar system. While this is a low probability scenario, it is not outside the realm of possibility. There are countless rogue gas giants drifting through interstellar space, and many may have once held positions much like Jupiter's. To lose Jupiter would be to lose the solar system's anchor. Not only would Earth become more vulnerable to impacts, but the gravitational equilibrium of the entire system could unravel. Mars and Earth might experience orbital instabilities. The asteroid belt could scatter. The moons of Jupiter, especially Europa and Ganymede, would be flung into isolation or destruction, and the solar system would be fundamentally changed, forever. In the silent reaches of space, power is not always visible. It resides in mass, in motion, in gravity. Jupiter exerts this silent power without fanfare, holding together a complex system that teeters on the edge of chaos. It is both guardian and potential threat, a duality born of its immense scale. As we ponder the possibilities of a stellar encounter, it becomes clear that Jupiter is the keystone. If Proxima Centauri or another interstellar traveler enters our domain, Jupiter's fate will be the fulcrum upon which everything else turns in the next chapter. We'll look back in time at historical stellar flybys, moments when other stars may have come close to our solar system, leaving subtle yet significant imprints on the cosmic landscape. Through these ancient encounters, we may find clues to the future that awaits. Chapter 4: Close Encounters of the Stellar Kind. Past visitors to our system. The idea of stars passing near our solar system may seem far-fetched, something confined to science fiction or theoretical modeling. But the truth is more astonishing. It has already happened more than once across the vast timeline of the galaxy. Other stars have silently drifted through the outskirts of our solar system, sometimes leaving behind faint traces of their passage. These cosmic near misses are not just astronomical curiosities. They are warnings. They tell us that stellar encounters are not only possible. The best documented of these encounters occurred just 70,000 years ago. That may sound ancient to us, but it is a mere blink in astronomical terms. At that time, Scholz's star, a faint binary system composed of a red dwarf and a brown dwarf, passed within 0.8 light-years of the Sun. That distance may seem vast, but it's well within the outer boundary of the Oort cloud, a distant, spherical shell of icy debris that surrounds the solar system and stretches out to nearly a light-year from the Sun. Although Scholz's star was relatively small and low in mass, its passage may have stirred the orbits of countless comets resting in the Oort cloud. Some of those icy bodies might have been nudged inward, beginning long, slow journeys toward the inner solar system, journeys that could still be unfolding today. Even without dramatic consequences, the very fact that such an event occurred so recently reminds us that the solar system is not isolated. It lives within a galaxy full of wandering stars, each following its own path across the cosmic sea. But Scholz's star wasn't the first. Astronomers studying stellar trajectories have found several candidates for ancient flybys. One particularly intriguing example is Gliese 710, an orange dwarf star located about 63 light-years away. Based on current trajectory calculations, Gliese 710 is expected to pass dangerously close to our solar system in the future, within just 1.3 million years. Its projected distance, a mere 0.2 to 0.3 light-years, that places it firmly inside the Oort cloud dot, unlike Scholz's star. Gliese 710 is much more massive, meaning its gravitational impact could be substantial. When it arrives, it may unleash a torrent of comets toward the inner solar system, increasing the likelihood of impacts on Earth and the other planets. Simulations suggest that the comet influx could last for millions of years. It is not the kind of event that would be noticed overnight, but it would slowly, inexorably change the nature of our skies and possibly the history of life on Earth. These close stellar passages serve as a sort of cosmic roll call, each one brushing past our solar system in quiet procession. Most pass at safe distances, but others come near enough to matter. The outer solar system is especially vulnerable, sensitive to even the slightest gravitational disturbances. A passing star doesn't need to come anywhere near Earth to affect us. All it needs to do is tap the Earth, clouding the consequences ripple inward. Sometimes catastrophic evidence of past disturbances may also be found in the cratering history of Earth and the Moon. Some mass extinction events and bombardment periods align suspiciously well with estimated timelines of close stellar passages, while other forces like galactic tides or internal solar system dynamics could also be responsible. Stellar encounters remain compelling candidates. And what about rogue planets' massive bodies, drifting through interstellar space without a star? Many of them are believed to be the result of violent gravitational encounters. These planets were likely ejected from their home systems after a close stellar flyby or interaction with a giant like Jupiter. It's a stark reminder that when stars pass too close, they can do more than disturb comets. They can rewrite entire planetary systems. The galaxy is not a static place. It's a dynamic, fluid environment where stars drift, loop, and occasionally trespass. Some encounters are gentle nudges, others are full-blown disruptions. For now, our solar system remains relatively tranquil. Our nearest neighbor has not yet made such a close pass, but its motion, influenced by gravitational tides and the Alpha Centauri system, could bring it nearer in the distant future. Should that happen, its massive though modest, could prove enough to disturb Jupiter's delicate gravitational dominion. The lesson of Scholz's star and Gliese 710 is clear. Distance is not permanence. What is far today can be dangerously close tomorrow. In the next chapter, we'll delve deeper into the science of stellar motion and chaos theory. How do astronomers predict such events? How far ahead can we truly see in this vast gravitational puzzle? And is it even possible to know with certainty whether a star like Proxima Centauri is destined to reshape our world? Chapter 5: Stellar Drift and chaos theory, predicting the unpredictable in the vastness of space, where distances are measured in light years and time in eons. It's easy to believe that everything moves with cold precision, that the universe is a perfect machine governed by unbreakable rules. And to some extent, it is. Gravity, mass, and motion follow the laws of physics with astonishing consistency. But when it comes to predicting the future paths of stars and the consequences of their journey, certainty begins to unravel. In the gravitational symphony of the cosmos, even the smallest note can eventually throw the entire orchestra into discord. This is where stellar drift meets chaos theory, and where astronomy becomes an exercise not just in observation, but in probabilistic imagination at its core. Stellar drift is simply the movement of stars through the galaxy. Every star orbits the center of the Milky Way, including our Sun. These motions are shaped by the galaxy's gravity, the influence of nearby stars, and even the ghostly presence of dark matter. Stars don't just orbit in neat circles, they bob and weave through the galactic plane, pulled subtly by invisible forces. And over millions or billions of years, these paths curve, shift, and twist in ways that make long-term prediction astonishingly complex. To map these movements, astronomers use detailed measurements of a star's radial velocity, its speed toward or away from Earth, proper motion, its apparent motion across the sky, and parallax, the slight shift in position due to Earth's orbit. Instruments like the Gaia Space Observatory have revolutionized this field, providing unprecedented data on over 1 billion stars. With Gaia, astronomers can project where a star will be in the future, where it was in the past, with extraordinary precision. But precision has limits. The deeper we look into time, the wider the margins of error grow. Why? Because of chaos theory, the idea that even in systems governed by deterministic laws, tiny variations in initial conditions can lead to vastly different outcomes. This concept, sometimes called the butterfly effect, is not just for weather, patterns, or stock markets. It applies just as powerfully to the cosmos. Imagine calculating the orbit of a star like Proxima Centauri. At first, the data is solid. We know its speed, direction, and position to many decimal places. But over 1 million years, or 1 billion, those decimals begin to matter. A rounding error here, a missing gravitational nudge there, and the predicted trajectory begins to diverge from reality. In time, the range of possibilities fans out like branches on a tree. We can still speak of probabilities, of likely paths and close approaches, but certainty dissolves into a cloud of maybe. The solar system itself is a chaotic system. Over long enough timescales, the gravitational interactions among the planets can cause their orbits to shift in unpredictable ways. Jupiter and Saturn, in particular, play a leading role in this dynamic. Their massive gravitational fields cause small but cumulative changes in the orbits of the inner planets. And in simulations that run forward billions of years, Earth's orbit, even its axial tilt, can become unstable. The system does not collapse, but it breathes, oscillates, and occasionally teeters on the edge of chaos. Add a passing star to this already delicate equation, and you amplify the chaos. The gravitational tug of a flyby, even from a small star like Proxima, could tip the balance, shifting planetary orbits ever so slightly enough, perhaps, to set off cascading changes over the millennia to follow. But can we know if such an event is coming? Can we predict whether Proxima Centauri will one day drift too close? The answer is partially. With current data, astronomers have created models that track Proxima's orbit within the Alpha Centauri system and relative to our Sun. These models suggest that while Proxima is currently moving away, perturbations from its companion stars and the galactic environment could redirect it over time. Some long-term simulations place it passing within 0.5 light-years of the Sun millions of years from now. Others show it veering harmlessly off in some scenarios. Proxima passes close enough to disturb the Oort cloud, but not the inner solar system. In more extreme versions, it penetrates deeper, perhaps even close enough to affect Jupiter's orbit. These outcomes are rare, but not impossible. The probability may be low, but the consequences would be enormous. Astronomers must therefore think in terms of statistical futures, not singular destinies. Much like weather forecasters use cone projections for hurricanes, space scientists project gravitational cones of possible future positions. Inside these cones lie futures in which nothing changes and others in which everything does. And here lies the strange beauty of cosmic prediction. The more we learn, the more we realize how fragile our knowledge truly is. For all our models and measurements, there remains an unknowable quality to deep time. The galaxy is a living system, evolving and shifting beyond the limits of our foresight. Jupiter, the mighty anchor of our solar system, may seem immovable. But if a star like Proxima enters the field, even on a distant trajectory, the future could begin to rewrite itself. The ripples would begin on the Aegis comets, subtle orbital drifts, but over time they could reach the core. The shield could become the spark in the next chapter. We'll explore that very possibility. What happens if Proxima's trajectory bends toward the Sun? What celestial dynamics could bring it nearer, and how close is too close? Chapter 6: The Long Game. Proxima's possible trajectory toward our Sun. from its quiet place in the southern sky. Proxima Centauri appears harmless, just a dim red dot, invisible to the naked eye. But in the language of the cosmos, motion is everything. No star is ever truly still. And Proxima, bound only loosely to its binary companions Alpha Centauri A and B, is subject to the subtle yet relentless forces of galactic drift. Over millions, perhaps billions of years, its path could shift, carrying it closer to the very heart of our solar system. But what would need to happen for this faint red dwarf to become a real threat? How could a star so small, so far away, alter its course enough to disturb Jupiter or even the Sun's entire planetary retinue? The answer lies in understanding both the galactic environment and the delicate mechanics of celestial trajectories. Proxima Centauri currently orbits Alpha Centauri A and B in a vast, elongated arc spanning tens of thousands of astronomical units. Its orbit is weakly bound, and small perturbations like passing stars or interactions with dark matter can nudge it off course. In the galactic frame, Proxima isn't just circling two stars, it's also orbiting the Milky Way's center, along with our entire solar system, embedded in a grand spiral that spans over 100,000 light-years. Within this spiral, everything moves. Stars shift, clouds of gas swirl. Proxima, like all stars, is swept along in this current, sometimes gently steered, sometimes pulled in new directions by forces too faint to detect from Earth. Over long enough timescales, its orbital path is not a line, but a corridor of probabilities. Astronomers model these probabilities using advanced speculations, mathematical reconstructions of how stars move through the galaxy. By inputting Proxima's mass, velocity, and position, along with data from the Gaia mission, researchers can project thousands of years into the future with fair accuracy. But beyond a certain point, typically several million years, chaos. Theory begins to unravel the clarity. The model doesn't yield a single trajectory, but a swarm of possible futures. Within that swarm are paths that take Proxima closer to the Sun. One of the more notable simulations shows Proxima passing within 0.5 light-years of the Sun, somewhere between 1 and 5 million years from now. That's well within the Oort clouder realm, packed with icy objects sensitive to any gravitational whisper. Should Proxima reach even 0.2 light-years, the potential for widespread disruption increases dramatically. At such a distance, its gravitational pull could stir not only comets, but possibly nudge the orbits of the outer planets. And with just the right angle and momentum, its influence could ripple inward, touching even Jupiter. Even more extreme scenarios while less probable, cannot be entirely ruled out. Galactic tides, the gravitational pull of the Milky Way's mass, act like invisible fingers, slowly tugging on star systems. If these tides, combined with local stellar interactions, shift Proxima's orbit enough, it could be drawn into a direct approach within 0.1 light-years or closer. At that distance, Proxima would become an undeniable force in the structure of our solar system. But how likely is such a close pass? The current consensus among astronomers is that a dangerously close flyby from Proxima is unlikely, but not impossible. Its trajectory today suggests a path moving away from the Sun. However, the long-term influences acting on its orbit are poorly understood. The gravitational tug of Alpha Centauri A and B could either stabilize or destabilize its motion. At the unknown mass and distribution of dark matter still invisible to our instruments, and the future becomes a blur of options. There is also the role of local stellar density. Our region of the galaxy, known as the local bubble, is relatively sparse. But stars do move through it, and gravitational interactions between nearby stars can accumulate over time, gradually deflecting or reshaping trajectories. In this long game of cosmic billiards, a small interaction today might mean a close encounter millions of years from now. The question, then, is not whether Proxima Centauri will come dangerously close, whether we are capable of foreseeing it. The timeline is immense, the uncertainties daunting. Yet if such an event were on the distant horizon, its effects would begin subtly. The first signs might appear in the shifting paths of distant comets, or in slight anomalies in Jupiter's motion. The solar system, finely balanced, would whisper before it screamed. A future flyby by Proxima would not be a sudden impact. It would be a slow warping of the gravitational fabric, an unraveling of orbits over millennia. It would be felt first at the edges, in the drifting of ancient comets, and then deepen inward, affecting moons, planets, and finally, the configuration of the solar system itself. In the next chapter, we'll leave the realm of probabilities and explore consequences. What actually happens when stars pass this close? What do real cosmic collisions look like? Could Jupiter survive such a disturbance? Chapter 7: Cosmic Collisions. What happens when stars interfere with planets? Stars are scattered so far apart that direct collisions are vanishingly rare. But not all interactions require impact. In the world of astrophysics, proximity is power, and the gravitational fields of stars are like invisible hands capable of disrupting entire planetary systems long before a single object comes into view. So, what really happens when stars pass close enough to disturb each other's realms? Imagine two stars moving through the galaxy. Each carries its own retinue of planets, asteroids, comets, and debris, gravitational bubble, held together by mass and motion. When those bubbles begin to overlap, even at distances of trillions of kilometers, the gravitational equations shift. The most fragile elements, the icy comets at the system's edge, the distant gas giants, are the first to respond. Their orbits elongate, twist, or become unstable. Some are drawn outward. Others are slung inward. Occasionally, entire planets are ejected, cut loose from their stars, and set adrift into the galactic void. Astronomers have observed the after effects of such events. There are rogue planets, massive worlds without a star, wandering alone between the stars. Many of these were likely born in stable systems, only to be expelled by powerful gravitational disruptions, sometimes from interactions with a passing star. Their orbits were distorted to such extremes that their parent stars could no longer hold them. These planets now float in perpetual night, reminders of how delicate a planetary system truly is. In simulated collisions between star systems, scientists have seen that gas giants like Jupiter are especially vulnerable because they orbit at large distances and possess considerable mass. They are the perfect targets for perturbation. A passing star can easily dislodge a gas giant's orbit, pulling it outward, slinging it into an elliptical path, or flinging it into interstellar space altogether. Sometimes the gas giant stays bound, but the chain reaction it triggers is enough to destabilize the inner planets, including Earth-like worlds. Even more dramatically, in some simulations, gas giants are pulled toward their parent stars, becoming hot Jupiters that orbit dangerously close to their suns. In others, they enter a chaotic phase, wandering unpredictably through their own systems, destroying moons and scattering smaller bodies like cosmic wrecking balls. These are not just thought experiments. In exoplanetary studies, astronomers have discovered numerous hot Jupiters, many of which defy expectations. Their existence suggests violent past histories of gravitational trauma, migration, and orbital disruption. Past collisions, others spin at abnormal angles or orbit in the opposite direction of their star's rotation. These are signs that something massive interfered long ago. Now apply that logic to our own system. If Proxima Centauri were to pass close enough within 0.2 or even 0.1 light-years, its gravitational influence could tug on Jupiter ever so slightly. And while Jupiter's immense mass gives it resilience, that very mass makes it more likely to respond. Its gravitational footprint would shift, pulling moons out of alignment, perturbing Saturn and Uranus, and potentially disturbing the asteroid belt and even Earth's orbit in extreme cases. Jupiter could be nudged into a new trajectory, perhaps inward, toward the Sun, heating its atmosphere and threatening inner planets with gravitational chaos. Or it could be flung outward into a distant elliptical orbit, transforming from a guardian into a distant, cold rogue. And in the most extreme case, it could be launched entirely out of the solar system, lost to the dark between the stars. These events unfold slowly over thousands or even millions of years. But their effects are cumulative and irreversible. Once the gravitational balance is disturbed, the system evolves into something new, something unpredictable. The moons of Jupiter would be particularly at risk. Stripped of their stable orbit, they might collide, crash into Jupiter itself, or be lost to space. Some could fall into the Sun. Others might become independent dwarf planets, wandering orphaned across the system. A few might be captured by other planets, transforming the very structure of the solar system's satellite network in planetary systems. Stability is not a given. It is an achievement, one constantly maintained by the intricate balance of mass, distance, and motion. When a star like Proxima draws near, it does not need to touch. Its presence alone is enough to unravel that balance. In the next chapter, we'll examine the hypothetical clash: Jupiter versus Proxima Centauri. What would happen in a head-to-head gravitational encounter? Which force would dominate hand? What would the solar system look like in the aftermath? Chapter 8: Jupiter versus Proxima. The scale and power of celestial forces in a universe defined by gravity and motion. Power is not always obvious. It can reside in the brightness of a star, the spin of a black hole, or the silent mass of a gas giant. To the unaided eye, Proxima Centauri appears insignificant, dim, small, barely a whisper in the sky. Jupiter, on the other hand, glows brightly in our night, dominating the solar system's planetary cast. But how would these two cosmic bodies compare in a direct gravitational showdown? Let's begin with scale. Jupiter is massive enormously. So, by planetary standards, it holds more than twice the mass of all other planets combined, exerting a gravitational influence that reaches far beyond its immediate orbit. Its presence carves gaps in the asteroid belt, shepherds the orbits of comets, and keeps its dozens of moons in a tight, resonant dance. It acts as a protector to Earth by capturing or deflecting potential impactors. It is, in short, the heavyweight champion of the solar system. But next to a star, even Jupiter, Bose, Proxima Centauri. Though only about 12% the mass of the Sun, still outweighs Jupiter by a factor of nearly 150. It is dense and self-luminous, powered by nuclear fusion, something no planet can claim. Its mass gives it an extended reach. Even at vast distances, its gravitational influence is far from negligible. And when a star moves near another system, the scale of its impact depends not just on proximity, but on the angle, speed, and direction of its trajectory. If Proxima were to pass within 0.2 light-years of the Sun, the competition wouldn't be direct in the way we imagine. This isn't a clash of titans colliding like celestial billiard balls. It's more like two massive objects gliding past one another, subtly pulling on everything between them. And in that quiet gravitational whisper, profound changes can begin. Jupiter, due to its massive orbit and strong gravitational field, would be one of the first major bodies to feel Proxima's encroaching presence. But whether it resists or yields depends on several key variables. Distance. The closer Proxima comes, the stronger its gravitational effect. At 0.1 light-years, Jupiter's orbit could stretch or distort. At 0.05 light-years, it could become unstable, perhaps even chaotic. Relative velocity. A fast pass may induce temporary disruption, like a tidal wave that crashes and recedes. A slow pass, however, could linger, increasing the chances of orbital capture, ejection, or resonant interactions. Approach vector. A frontal encounter might cancel or magnify Jupiter's orbital momentum. Pass from behind could accelerate it, while one from the side could tilt its orbit or shift its angular momentum in strange ways. Astronomers use simulations to test such scenarios. One set of models reveals that in close passage events, gas giants like Jupiter can behave in startlingly diverse ways. Some are nudged inward, where they spiral toward their stars and become hot Jupiters. Others are sent outward, grazing the edge of their systems before being pulled back in. A few are completely ejected, becoming rogue planets that wander the galaxy in darkness. In the case of Jupiter, its fate would depend on timing. If Proxima arrived at a moment when the gravitational harmonics of the solar system were already vulnerable due to orbital resonances or minor instabilities, then the effect could be magnified. A passing nudge could become a full-fledged shove. Jupiter might shift just enough to disturb Saturn, then Uranus, and so on. The outer system would cascade into a new alignment or unravel entirely. And yet, it is not only Jupiter at risk. Proxima's gravity wouldn't target a single planet. It would press upon the entire heliosphere, the vast bubble formed by the Sun's solar wind. Comets, dwarf planets, the Oort cloud and the Kuiper belt hall, would feel the approach. But it is Jupiter's centrality, its stabilizing role, that makes its response the most consequential. If Proxima's pass nudged Jupiter even slightly inward, Earth's own orbit could begin to oscillate. Over millennia, this might affect our climate, axial tilt, or even orbital stability. A planet billions of kilometers away could become the trigger for an earthbound crisis. On the other hand, if Jupiter were ejected, it could take several of its moons with it, perhaps even Europa or Ganymede, leaving the solar system permanently altered. And Proxima, the quiet traveler, would sail on, having rewritten the lives of worlds without ever making contact. The lesson is clear. Gravitational power does not require proximity or violence. A quiet drift through space, guided by mass and mass momentum, can be more transformative than any direct collision. In the cosmic arena, even a near miss is enough to change everything. In the next chapter, we'll explore what that change looks like. How would the balance of the solar system begin to shift if Jupiter's orbit were disturbed? Could the system realign itself, or would everything begin to unravel? Chapter 9. A shift in the balance. How a stellar encounter could destabilize Jupiter, the solar system. For all its grandeur and apparent permanence, is a delicately balanced construct. The orbits of the planets, the dance of their moons, and the long-term harmony of gravitational forces all stem from a foundational equilibrium system sculpted over billions of years. At the heart of this balance lies Jupiter, the giant whose mass governs more than just its own fate. If Proxima Centauri were to pass near enough to disturb Jupiter's path, the solar system would begin to shift, not immediately, not violently, but with an unstoppable, quiet drift into disorder. To understand how that would unfold, we must first grasp how Jupiter stabilizes the system. Its massive gravitational pull regulates the motion of countless bodies. It keeps the asteroid belt from coalescing into a planet. It protects Earth from many incoming comets by capturing or deflecting them. It helps maintain resonant orbits among the other gas giants, preventing collisions and wild orbital variations. In short, Jupiter is both a barrier and a conductor, a planetary maestro orchestrating celestial order. Now imagine that order faltering. Let us suppose that Proxima Centauri, in one of its closer model trajectories, passes within 0.1 light-years of the Sun. The disturbance it introduces is not immediate. It begins with the faintest alteration, perhaps a slight increase in Jupiter's orbital eccentricity. From nearly circular, Jupiter's path becomes slightly elliptical. The change is small fractions of a percent, but its effects ripple outward in the first thousands of years. The consequences are subtle, moons experience new tidal stresses. The orbital relationships between Jupiter, Saturn, Uranus, and Neptune begin to drift out of resonance. These gas giants are locked in complex gravitational rhythms, like gears in a watch. Disrupting one throws off the entire mechanism. Saturn might start to oscillate, its orbit pulled slightly out of sync. This, in turn, affects Uranus and Neptune, and soon the entire outer solar system is wobbling ever so slightly. These are not random changes. They follow the laws of orbital mechanics. But as their eccentricities increase, their perihelia and aphelia start to intersect in new, untested configurations. Jupiter, now off its original track, may gradually move either closer to the Sun or drift farther away. If it migrates inward, even slightly, the asteroid belt could be pulled apart, flinging debris toward the inner planets. Earth might face a new bombardment era, as ancient rocks from the early solar system rain down over millennia. If Jupiter migrates outward, could destabilize the Kuiper belt, dislodging Pluto and other icy worlds, while weakening its own gravitational hold on some of its larger moons. In time, Ganymede or Callisto might fall into chaotic orbits, sliding, escaping, or being drawn into resonance patterns that trigger geologic upheaval. And then comes the worst case scenario. Jupiter enters a chaotic phase. This is a real possibility. In long-term orbital simulations, once pushed past a threshold of stability, Jupiter's orbit could begin to wander. It might develop a highly elliptical path that crosses those of Saturn or even Mars. Planet-planet interactions could intensify, causing slingshot-like energy transfers. Jupiter, once a calming presence, would become a wild Cardan object too massive to ignore. Now, acting without restraint, even without collision, such chaos changes everything. Mars might be ejected from the system. Earth's orbit could stretch or compress, altering our climate so drastically that life is no longer sustainable. Venus and Mercury could collide. Moons might be flung into deep space or crash into their planets. The solar system, over a few million years, would become unrecognizable, and Jupiter itself, it might not survive in its current role. In some simulations, gas giants destabilized by stellar encounters are ultimately ejected from their systems, flung into the galaxy as rogue planets. Others spiral inward, either evaporating in close orbits or being consumed by their stars. In both cases, the protective role is lost with it, the relative safety of Earth. The unraveling is not fast. It is not cinematic. It is silent, glacial, and final. A cosmic realignment whose seeds are planted by a single gravitational whisper in the next chapter. we will descend into a darker possibility, still one where Jupiter's destabilization sets off a chain of impacts and orbital disasters. If Jupiter falls from its position as guardian, what are the risks to Earth? And could this chain of events become an extinction-level threat? Chapter 10. Earth in the Crossfire. The domino effect of Jupiter's fall for billions of years. Earth has thrived under the protective shadow of Jupiter. Its colossal mass and strategic position between the inner and outer solar system have acted as a gravitational shield, deflecting or capturing many of the asteroids and comets that might otherwise have struck our fragile blue world. But if that guardian were to falter even slightly, the ripple effects could transform Earth's future from safe haven to target. This is the terrifying consequence of a destabilized Jupiter. Earth would be caught in the crossfire of celestial chaos. Let's return to the scenario previously set in motion. Proxima Centauri glides past the solar system within a critically close range. Jupiter's orbit is altered just enough to begin drifting its shape, becoming more elliptical. Its orbital period gradually shortening or lengthening. At first, it's just a mild eccentricity, invisible to the human eye, undetectable in the night sky. But on a cosmic scale, the balance begins to tilt. One of the first victims is the asteroid belt. Jupiter's new orbit disrupts the complex gravitational relationships that keep the belt stable. Normally, Jupiter maintains clear zones of resonance, where asteroids are swept into predictable orbits out of them entirely. These resonance gaps, like the famous Kirkwood gaps, are a direct product of Jupiter's gravitational rhythm. Disturb that rhythm, and those unsafe pockets of space become volatile. Asteroids begin to drift inward, one by one at first, then in clusters. Some enter the inner solar system, following unpredictable paths. The chance of a major impact on Earth, already a statistical certainty over long timescales, increases dramatically. A new late heavy bombardment could be triggered, reminiscent of the catastrophic era that scarred the Moon and reset Earth's surface billions of years ago. But impacts are just the beginning. If Jupiter's orbital drift grows more extreme, could eventually enter resonance with Earth. In the worst-case simulations, this leads to periodic gravitational tugs that amplify Earth's orbital eccentricity. Earth's orbit begins to stretch not into chaos, but into a slow-motion instability. Seasons intensify. Summers grow hotter, winters colder. Over thousands of years, the climate begins to lurch from one extreme to another, stressing ecosystems, shifting ocean currents, and testing the adaptability of life at a critical point. Earth may no longer remain in the habitable zone. The subtle shift in distance from the sun, just a few percent, is enough to swing the balance. Photosynthesis falters. Ice caps expand or collapse. The biosphere enters a cascade of crises. Mass extinctions become more likely not because of a singular cataclysm, but because the planetary system that nurtured life begins to betray it. And what if Jupiter's instability triggers chain reactions among the other planets? Saturn's orbit might also drift, entering its own resonance with Jupiter. Their combined gravitational effects could then reach Earth with greater force. Venus, already a chaotic actor due to its retrograde rotation and dense atmosphere, might nudge further inward or become gravitationally entangled with Earth's path. The risk of planetary near misses or even collisions, while exceedingly rare in stable conditions, rises dramatically in a perturbed system. Earth's moon, too, could be affected. While tightly bound to our planet, its orbit is slowly evolving. Gravitational disruptions elsewhere in the system could cause slight variations in the moon's path, affecting tidal forces, day length, and rotational stability. Over millennia, these effects accumulate. A small change in the moon's distance alters ocean dynamics, weather systems, and potentially the stability of Earth's axial tilt, the very factor that controls our seasons. And then there's the wild card. Comet, as the Oort cloud is stirred by Proxima's influence and Jupiter's destabilization. Long-period comets begin arriving with greater frequency and less predictability. Some swing harmlessly by, others, drawn in by a weakened Jupiter, plunge toward Earth. A single impact of sufficient size, 10 to 15 kilometers across, could wipe out most life, as it did for the dinosaurs. If multiple impacts occur over a span of centuries or millennia, recovery becomes nearly impossible. The result is not instant annihilation, but gradual devastation. Civilizations would rise and fall against a background of environmental stress. Agriculture might fail. Ocean ecosystems could collapse. Pandemics would spread more easily in a warming and cooling world. Survivors would be forced to adapt to a planet in flux, till eventually the climate becomes too chaotic to support. Complex life, it's a sobering vision, one that begins not with violence, but with a mere nudge to a gas giant, a passing star, a moment in cosmic time. And yet, within this darkness, there is still a sliver of light. The very models that show Earth's vulnerability also show the solar system's resilience, its ability to absorb certain disruptions, to stabilize over time. If the disturbance to Jupiter is minor, the system may realign. Earth may endure. Life, always persistent, might adapt, evolve, and flourish in new forms. But that resilience has limits. And if Proxima Centauri pushes Jupiter too far, those limits may be tested like never before. In the next chapter, we'll peer even deeper into the abyss. Could Jupiter itself collide with another planet or even be swallowed by the sun? When the balance breaks, how far can the chaos go? Chapter 11. Into the Abyss. Could Jupiter fall into the sun or collide with a planet? In the intricate ballet of the solar system, Jupiter has always been the giant in the wings, a colossal presence that shapes the rhythm without ever stepping out of line. But if its orbit were destabilized by an external force like Proxima Centauri, that careful choreography could unravel. And when the largest planet in the system begins to sway, the consequences may cascade into the unthinkable. Could Jupiter, the great stabilizer, become a destructive agent, even to the point of falling into the sun or colliding with another planet? Though it sounds like science fiction, orbital migration is a well-documented phenomenon in planetary systems. Many of the exoplanets we've discovered, particularly the enigmatic hot Jupiters, are gas giants orbiting perilously close to their parent stars. Their existence implies that these planets did not form in such locations, but migrated inward due to gravitational interactions there with the remnants of their planetary disks. Or, more dramatically, through encounters with other stars or massive bodies. If Jupiter's orbit were altered, let's say, by just a few %, its trajectory might shift gradually inward. This wouldn't be a rapid descent, but a slow, spiraling inward migration over millions of years. With each revolution, its orbital energy would change, nudging it closer to the sun. Such a process would begin subtly. Jupiter's distance from the sun, currently about 778 million kilometers, might decrease by a few thousand kilometers each century. The gas giant would grow brighter in our sky. Its gravitational grip would stretch differently across the system, and tidal interactions with the sun could start to heat its outer layers. If the migration continues, Jupiter might eventually cross the orbit of Mars, leading to planetary resonances never before encountered. Mars's own orbit could be destabilized, or worse, if orbital paths intersect the two planets might come dangerously close. And though the idea of a full-blown planetary collision may seem impossible, models of other systems suggest it is not. Planet-planet collisions, while rare, are a recognized consequence of dynamic chaos. If Jupiter's path were sufficiently perturbed, a close encounter with Mars or even Earth could, in theory, occur. The outcome would be catastrophic. Mars would be torn apart, its fragments scattered across the inner solar system, triggering secondary impacts and an irreversible chain of destruction, the more likely fate. However, in this hypothetical spiral is that Jupiter continues inward until it becomes a hot Jupiter gas giant orbiting at a fraction of an astronomical unit from the Sun. At this distance, Jupiter would experience intense solar radiation, and its atmosphere would begin to boil away, producing massive trails of ionized gas. Tidal forces would elongate the planet, stretching its shape into an oblate spheroid and heating its core. Over time, its mass would decrease, its atmosphere stripped layer by layer. Eventually, Jupiter might reach a critical Roche limit where the Sun's gravitational pull overcomes Jupiter's self-gravity. At that point, the gas giant could begin to disintegrate, forming an accretion disk of glowing matter around the Sunna cosmic funeral pyre of hydrogen and helium. From Earth, this event would create a stunning but terrifying sky, a blazing ring of vaporized planetary remnants slowly spiraling into the star. Alternatively, Jupiter could avoid disintegration and simply plunge into the Sun, absorbed by its mass. While the Sun is vast enough to endure such an impact without significant structural change, the release of energy would be considerable. The infusion of Jupiter's mass might disturb the Sun's internal dynamics for a time, possibly affecting solar output, at least temporarily. Solar flares or magnetic field shifts could spike, increasing radiation storms that reach Earth and disrupt our atmosphere. But what if Jupiter doesn't fall into the Sun, but instead collides with another gas giant? Orbits begin to overlap. A slow-motion gravitational spiral could draw them together. The resulting merger would be unlike anything ever witnessed in our solar system's history. The planets would approach each other over centuries, their gravity deforming their atmospheres, creating tides and shock waves that span tens of thousands of kilometers. Eventually, the collision would release immense thermal and kinetic energy, heating the merged body to incandescence. The new object, likely more massive than either predecessor, could ignite fusion briefly in its corpusing a failed star or brown dwarf. The outer planets and moons would be cast into chaos as the new mass center reshaped the entire solar system's gravitational map. Earth, in this scenario, might find itself ejected, pulled into a new orbit, or roasted by gravitational tidal waves radiating from the impact site. These are extreme events, and the probabilities are low. But the fragility of balance means that all it takes is one small disturbance, one passing star, one slight nudge for the solar system's architecture to begin to twist toward catastrophe. In the next chapter, we'll examine how these outcomes fit into the bigger picture of planetary system evolution. Are systems like ours truly rare? Or is celestial upheaval the norm, and our moment of peace the real anomaly? Chapter 12. Solar Systems in Flux. Are we the exception or the rule? When we gaze into the night sky, we often imagine the stars as distant suns, each with their own orderly retinue of planets, moons, and perhaps even life. But over the past few decades, as humanity has discovered thousands of exoplanets, a new picture has begun to emerge, one that challenges our assumptions. Our solar system, with its long-term stability and wide planetary spacing, may be the cosmic anomaly. In truth, most planetary systems we observe are nothing like ours. Many feature hot, Jupiter's massive gas giants that orbit extremely close to their stars, often completing a full revolution in just a few days. These planets are scorched by radiation, bloated by tidal heating, and frequently locked in orbits that suggest violent migration. Some systems contain planets that are tilted at bizarre angles or that orbit in the opposite direction of their star's rotation. Others show evidence of past collisions, orbital flips, or planetary ejections. Why is this so common? Because chaos is the rule in planetary formation. When a star forms, the leftover gas and dust swirl into a disk, clumping into planets over millions of years. These forming planets don't simply fall into line, they compete. They push, pull, and occasionally destroy one another. The early solar system was no exception. Evidence suggests that multiple large protoplanets once roamed our system. One such body may have collided with the young Earth, giving birth to the Moon. Another may have been hurled into the Sun or flung into deep space. So what made our system settle down? The answer likely lies with Jupiter. Its massive presence shaped the evolution of the entire planetary layout. Jupiter may have migrated inward slightly during its youth, but it never made the full plunge toward the Sun like so many exoplanetary giants. It also appears to have shielded the inner planets from excessive bombardment, sweeping up or redirecting dangerous material. In doing so, it allowed Earth to remain in the habitable zone, largely untouched by catastrophic events after the early turbulence subsided. Yet, even that stability may be temporary. Astronomers now recognize that long-term chaos is built into every gravitational system. Our solar system is stable for now, but simulations that project billions of years into the future show the possibility of dramatic changes. Mercury's orbit, for instance, is slowly becoming more eccentric and could, in tens of millions of years, cross paths with Venus. Jupiter and Saturn may one day fall out of resonance, setting off a chain reaction. Over immense spans of time, Even the most peaceful system becomes unpredictable. In this context, the hypothetical disturbance from Proxima Centauri becomes not an outlier, but part of a greater cosmic rhythm cycle in which periodic disruption is inevitable. Close stellar passes are not rare on astronomical timescales. In fact, simulations suggest that stars in the Milky Way experience such encounters every few million years. Many systems likely undergo complete architectural reshuffling. Some lose planets, others gain them through capture, and many end up with rogue worlds adrift in interstellar space. There's also mounting evidence that binary and multiple star systems, which make up the majority of the galaxy, have inherently more dynamic canned, unstable planetary configurations. With two or more suns tugging on each orbit, the odds of chaos are greatly increased. Planets are regularly thrown into new orbits or lost altogether. In that sense, the Earth's long stretch of habitability, some 4 billion years and counting, may be a precious window, not a norm. It may be the quiet in a storm that rages over cosmic eons. This perspective reframes the potential threat from Proxima Centauri. Rather than a freak event, it becomes a natural chapter in a much larger story of drift, interaction, and transformation that defines the life cycles of planetary systems. Jupiter's potential fall, Earth's vulnerability, and a slow unspooling of stability are all parts of that grand narrative. And whether Proxima is the agent of change or some other star in the distant future, the message is the same. Permanence is an illusion in the universe. All things shift. All systems evolve. In the next chapter, we'll consider one more profound question. If Jupiter were lost or transformed, could the solar system rebuild itself? Would the architecture collapse forever? Chapter 13. After Jupiter, can a planetary system heal? Jupiter has always been more than just a planet. A cosmic shield and a regulator of motion on a scale beyond human intuition. So what happens if that cornerstone is removed? Can the system realign itself, or would the loss of Jupiter spell the permanent unraveling of planetary order? To answer that, we must imagine the solar system without Jupiter. Perhaps the gas giant has been ejected by Proxima Centauri's distant yet powerful gravitational pull. Perhaps it spiraled into the sun or collided catastrophically with another planet. However it is lost, the result is the same. Over 300 Earth masses of gravitational influence vanish in a single cosmic heartbeat, and with it, the delicate balance that holds everything together is shaken. The most immediate effect would be felt in the asteroid belt. Jupiter's absence would cause chaos in this region, as the resonance patterns that currently maintain gaps and order among asteroids would dissolve. Collisions would become more frequent. Many would be sent inward toward the terrestrial planets. Earth, no longer protected, would face a renewed era of impacts, potentially rivaling the early heavy bombardment period that helped shape its crust. But the asteroid belt is only the first. Layer dot without Jupiter's gravitational damping effect. The orbital dynamics of the outer planets would begin to shift. Saturn, no longer held in resonant check, could drift. Its own moons, some of which are remarkably large and active, might fall into new, unstable paths. Uranus and Neptune, while distant, could feel the long-term effects as their resonance with Saturn adjusts. Even the Kuiper Belt, home to Pluto, Eris, and countless icy worlds would begin to stir. The belt's current architecture is partially shaped by Jupiter's ability to steer long-period objects into or away from stable zones. Without that steering, the outer solar system becomes a field of slow chaos, where small gravitational nudges over thousands of years add up to erratic migrations and even planetary ejections. Now consider Earth in simulations where Jupiter is artificially removed. Earth's orbit remains stable in the short term, but the long-term consequences are less certain. Saturn's growing influence, coupled with the unpredictable effects of minor planetary drift, may slowly shift Earth's orbital eccentricity. Climate would begin to change in response, not suddenly, but persistently. Ice ages could grow deeper, heat waves more intense, seasons increasingly erratic. And then there's the issue of cosmic debris. Jupiter currently absorbs or redirects a significant amount of incoming comets and interstellar bodies. Its gravitational field acts like a planetary sponge, attracting objects that might otherwise continue inward toward the Sun. Without Jupiter, these wanderers would proceed unchallenged, dramatically increasing the likelihood of cometary impacts across the inner solar system. This threat is not only physical, but also psychological for any intelligent species living on Earth. The sky would change. The rate of near-Earth's objects would rise. Telescopes would track more potential impactors. Civilizations, if present, would shift resources toward planetary defense. Entire generations might grow up under a permanent shadow of celestial risk. But amidst this unsettling vision, there is a glimmer of resilience. Planetary systems are not static. They adapt. In the long term, after the chaotic readjustment period, new resonances could emerge. Saturn might assume a more central role in gravitational regulation. Moons and minor bodies might be captured into new orbits. Earth, while more vulnerable, could settle into a new climate regime. Life, as it has done for billions of years, might evolve to meet the new conditions. In fact, Some simulations show that, even without Jupiter, the inner planets, including Earth, can survive for billions of years, depending on the exact nature of the disturbance. Chaos increases, but total collapse is not guaranteed. The system, while altered, may find a new kind of equilibrium, less ordered, more volatile, but still recognizable. It would be a different solar system, one born from loss, but not devoid of structure. A reminder that while gravity may bring destruction, it also builds anew. The planets might dance to a different rhythm, but they would still dance. In the next chapter, we'll ask a more speculative question. Could humanity, or its descendants, survive a future without Jupiter? And what technologies or strategies might allow us to adapt to a post-Jupiter world? Chapter 14: Humanity without Jupiter, adapting to a new cosmic order. For most of its existence, humanity has thrived without any awareness of Jupiter's role in its survival. The gas giant has quietly shaped the path of life on Earth, deflecting deadly asteroids, stabilizing planetary orbits, and regulating the cosmic traffic that threatens to intrude upon our fragile blue world. But what if that silent guardian were gone? Could humanity adapt to a future where the rules of the solar system have changed? The first and most immediate challenge would be planetary defense. With Jupiter no longer acting as a gravitational filter, Earth would be exposed to a higher influx of comets, asteroids, and interstellar debris. The statistical probability of a major impact ready, a long-term certainty, would increase significantly. This would force humanity to invest more aggressively in technologies to detect, deflect, or destroy incoming threats. Orbital observatories would be placed in strategic positions to provide early warnings. Earth-based and space-based missile systems, possibly using nuclear propulsion or kinetic impactors, would be developed as standard defense tools. Entire branches of government or interplanetary coalitions might arise solely to track and manage this cosmic threat. Asteroid mining and manipulation, already emerging as future industries, could evolve into planetary-scale security programs. But defense is only part of survival, as Jupiter's loss destabilizes the solar system over time. Earth itself might begin to experience more severe orbital drift and climate instability. The seasons could grow unpredictable. Ocean currents might reverse. The polar ice caps could expand or vanish entirely. Agricultural zones would shift, and long-standing ecosystems could collapse. These slow but relentless changes would demand a complete rethinking of how humanity inhabits the planet. In this new world, cities might become mobile or modular, capable of relocating with climate zones. Global food systems would need to rely More on vertical farming, synthetic biology, and resilient crops that can survive extreme temperature swings. Vast networks of underground and underwater habitats might emerge, shielded from solar storms and surface instability, and powered by geothermal or fusion energy. In extreme scenarios, Earth may become uninhabitable over millennia from a singular event, but from the compounding effects of orbital and climate shifts. Humanity, recognizing this trajectory, would begin looking outward, not just to Mars, but to the moons of Saturn and Uranus, to interstellar space, even to planetary engineering. Could we build a replacement for Jupiter? This may sound like fantasy, but theoretical engineering projects, the scale of planetary scale, mass drivers, orbital redirection systems, or artificial gravitational regulators could become conceivable for a Type II civilization on the card-shaped scale. We might attempt to reposition another gas giant, like Saturn, into a more stabilizing orbit, or construct gravitational anchors, massive space structures designed to replicate some of Jupiter's shielding role. Alternatively, humanity may simply learn to navigate a chaotic system, creating spacefaring societies that drift between planets, adapt to variable gravity, and move with the tides of celestial mechanics. Generation ships, orbital rings, and self-sufficient biospheres could become the new norm, not as emergency shelters, but as the default mode of existence. From a cultural perspective, the loss of Jupiter would not go unnoticed. Once a bright, constant object in our night sky, its absence would mark a turning point in planetary history. Art, literature, philosophy, and religion might grapple with its departure, interpreting it as an omen, a challenge, or a transformation. New myths would rise. Perhaps, to future generations, Jupiter would be remembered not just as a planet, but as a lost protector, a fallen titan whose sacrifice allowed life to flourish for a time. But humanity is defined by its resilience. We have survived ice ages, global extinctions, cosmic impacts, and environmental collapse. We've crossed deserts, oceans, and the void of space itself. And in a post-Jupiter world, we would face our greatest test yet, not against a visible enemy, but against the slow erosion of celestial balance. To survive, we must evolve, not just biologically, but technologically, socially, and philosophically. We must become a cosmic species capable of understanding and shaping the forces that once shaped us. In the next chapter, we'll turn our attention outward once more and ask, how would Proxima Centauri itself be affected by its encounter with our solar system? Could it capture any part of our system or leave with unexpected passengers of its own? Chapter 15. Proxima's Prize. Could our planets be captured by another star? When we imagine a star passing near our solar system, we tend to focus on the danger it poses to us, the disruption of orbits, the unbalancing of gravitational harmony, and the possibility of cosmic catastrophe. But what if the encounter works both ways? What if, instead of merely disturbing us, Proxima Centauri takes something with it? This is the concept of stellar captura, rare but real cosmic phenomenon in which a passing star, through sheer gravitational influence, pulls objects from one system into its own. Proxima Centauri, despite its relatively small size and mass, could become a cosmic thief as it approaches the outskirts of the solar system. Its gravity would begin to compete with the Sun's for dominion over distant objects. The first zone it would affect is the Oort cloud, a vast sphere of icy bodies located far beyond Pluto, extending up to 100,000 astronomical units from the Sun. These distant objects are only loosely bound to our star, held more by inertia than intimacy. If Proxima comes close enough, it could easily draw some of them into its own orbit, giving rise to a shared population of comets between the two stars. But what about something larger? Could Proxima steal an actual planet, Jupiter, or any outer gas giant is destabilized and flung outward during the encounter? It could pass into a gravitational limbong, longer firmly attached to the Sun, but not yet free of its influence. In this delicate state, Proxima's gravity could take over. If the trajectory is right and the velocity is low enough, Jupiter could be captured into orbit around Proxima, becoming a planetary exile giant far from the star that birthed it. This isn't just speculation. Simulations of close stellar flybys show that such captures, while rare, are possible under the right conditions. The resulting orbits are often wide, eccentric, and unstable, but for a time, the captured planet becomes part of a new system. Imagine Jupiter circling Proxima Centauri from one of its moons. The sky would look utterly alien. Proxima's dim, reddish glow would barely light the landscape. Solar radiation would be weak. But Jupiter's own internal heat might keep its larger moons like Europa or Ganymede geologically active. These worlds already thought to harbor subsurface oceans might survive in a marginal state of warmth. In such a configuration, the ingredients for life could persist long after the original system that nurtured them has been left behind. Proxima could even acquire multiple objects, small moons, dwarf planets, or rogue asteroids nudged into its path during the flyby. Over time, this new system might stabilize, giving Proxima a second generation of planetary companions. These visitors, born of another star, would become cosmic adoptees, carried into an entirely different stellar environment. But this scenario also raises a haunting possibility. Reverse abduction, just as Proxima could take from us, so too could we take from it. The gravitational interaction might sling one of Proxima's own planets or its theorized companions into our inner solar system. If such a body crosses Earth's path or settles into a distant orbit around the Sun, our planetary family could be forever changed. We might even gain a new planet, one born light years away. There's also the question of interstellar contamination. Captured bodies may carry different compositions, volatile ices, exotic isotopes, or even organic molecules unfamiliar to our chemistry. If life exists elsewhere in the galaxy, and if it hitches a ride on cometary fragments or icy moons, then a stellar flyby could act as a biological bridge, exchanging materials between solar systems. The encounter between stars becomes not just gravitational, but potentially biological. These ideas, while speculative, are grounded in the mathematics of orbital mechanics and the growing knowledge of how chaotic and fluid planetary systems truly are. In a galaxy with hundreds of billions of stars, such cosmic handshakes may be rare but inevitable. From a philosophical standpoint, the possibility of planetary exchange redefines our view of celestial identity. Star, would it still be ours? Would its moons still be considered part of the solar system's legacy? Or would they become citizens of a new star, rewriting their place in the history of the cosmos? And if Earth were one day to be flung outward Proxima or beyond, what would remain of our legacy? Would we carry our culture with us, our machines, our descendants? In the next chapter, we'll venture deeper into that idea. What if Earth itself were dislodged from the solar system and became a rogue world or was captured by another star? What would survival look like in the cold void between stars? Chapter 16. Earth Adrift. The possibility of a rogue planetary journey. The thought of Earth drifting alone through the cold, dark void of interstellar space is both terrifying and strangely mesmerizing. Without the sun's warmth and light, our planet would become a frozen wanderer, a rogue world cast adrift by the cosmic forces unleashed when Jupiter's stabilizing presence is lost, or when a stellar encounter like that of Proxima Centauri tears our planetary family apart. How could this happen? What would such a journey mean for the future of life, if it survives at all? And could Earth ever find a new home? The mechanisms to eject Earth from its orbit are complex but conceivable. In the chaos following a stellar flyby, Jupiter's gravitational grip weakens or vanishes, and the gravitational dance of the planets becomes erratic. A close encounter with another planet, Saturn, Mars, or even a captured object from Proxima Centauri impart enough energy to push Earth out of its stable orbit. Alternatively, the cumulative effect of increasing orbital eccentricity and resonance disruption might gradually spiral Earth outward until it escapes the Sun's pole entirely. Once free, Earth becomes a rogue planet, no longer tethered to a star dot in the darkness between stars. The surface temperature would plummet. The atmosphere would condense. Oceans might freeze solid, and life as we know it would face an existential crisis. Yet, even in this bleak scenario, survival might be possible. Scientists have theorized that rogue planets could maintain internal heat generated by radioactive decay and residual gravitational compression. This heat might be sufficient to keep subsurface oceans liquid beneath thick ice layers similar to moons like Europa or Enceladus within our solar system. Deep microbial life and possibly more complex organisms could persist in these hidden refuges. Moreover, Earth's atmosphere, though chilled, might provide some insulation. If greenhouse gases remain, they could trap enough warmth to sustain pockets of liquid water underground or in deep ocean trenches. But without solar energy, surface photosynthesis would end. Energy from chemical reactions and perhaps geothermal vents, ecosystems would shrink. But life is remarkably tenacious. Could humans survive such a fate? It is a question that strains the imagination. Survival would require advanced technologies, self-sustaining habitats deep underground or in orbit, hydroponic farms fed by artificial light, and life support systems capable of recycling air, water, and nutrients indefinitely. The psychological toll of living in eternal darkness would be immense. Alternatively, if Earth were captured by Proxima Centauri or another star during the stellar encounter, it might find itself in a new but alien solar environment. Proxima Centauri is a red dwarf, smaller and cooler than the Sun, emitting less energy. Earth's climate would change drastically, likely becoming much colder unless atmospheric conditions adapt. This scenario might offer a chance for the biosphere to recover, but it would require radical adaptations. Life would need to adjust to different solar spectra, possibly lower energy input and altered magnetic environments. From a cosmic perspective, rogue planets and captured worlds expand the definition of what it means to be a planet, a habitat, and a cradle for life. They are way stations of cosmic evolution, wandering through space, carrying the possibility of life across the galaxy. As humanity contemplates these remote possibilities, our understanding of survival extends beyond our planet, and star. It embraces a vision where life is not confined to a single solar orbit, but is a resilient traveler, capable of enduring the darkest and most uncertain journeys in the next chapter. Captured by Proxima Centauri, or cast into the interstellar medium band. What this means for the legacy of our solar system's giant. Chapter 17. Jupiter's New Home. The Fate of a Captured Giant, Jupiter. Once the undisputed monarch of the solar system could find itself cast adrift or bound to a new star, its fate intertwined with Proxima Centauri. What would become of the giant planet in such circumstances? Would it survive, adapt, or fade into obscurity as a cold, lonely wanderer? If captured by Proxima Centauri, Jupiter would enter a new gravitational relationship, second act of its cosmic journey. Orbiting a dim red dwarf, Jupiter's environment would change drastically. Proxima Centauri's lower luminosity means the planet would receive far less stellar energy than it does from our Sun. Its atmosphere would cool, contracting and becoming denser. Yet, Jupiter's immense internal heat, generated by slow gravitational contraction and residual formation energy, would continue to warm the planet from within. In this colder, darker setting, Jupiter's characteristic bands and storms might alter in appearance and intensity. The famous Great Red Spot, a gigantic storm larger than Earth, might weaken or transform under different atmospheric dynamics. Jupiter's moons, many of which may harbor subsurface oceans or geological activity, would also experience new conditions. Reduced solar radiation means less surface heating, but tidal interactions with Jupiter would persist, maintaining internal heat on moons like Europa and Io. These worlds could become even more intriguing as potential habitats. Warmed primarily by Jupiter's gravity rather than stellar energy, if Jupiter were ejected into interstellar space instead, the challenges multiply. Without any star to orbit, Jupiter would become a rogue planeta, wandering mass of gas and liquid drifting through the cold void. Over billions of years, it would slowly lose heat, its atmosphere contracting further. But its immense size and internal energy mean it would remain warm compared to smaller worlds, potentially maintaining a thick, dense atmosphere and liquid layers beneath. Such rogue gas giants might be common in the galaxy, but their isolation renders them dark and invisible to traditional observation methods. They could serve as unexpected waypoints for interstellar probes or habitats for future civilizations capable of harnessing their energy. Jupiter's loss from the solar system would leave a void, both gravitational and symbolic. Stabilizes planetary orbits, shields inner worlds from dangerous debris, and inspires wonder in the night sky. Yet, its new existence, whether as Proxima Centauri's captive or as a cold wanderer, reminds us of the impermanence of cosmic order. Planets and stars dance to gravity's tune, but the choreography is ever-changing. In the next chapter, we will look beyond the immediate solar system to the wider galactic neighborhood and explore how stellar encounters like Proxima's passage shape the evolution of planetary systems across the Milky Way. Chapter 18: Galactic Neighborhoods: The Role of Stellar Flybys in Planetary Evolution. The Milky Way is a vast, swirling galaxy home to hundreds of billions of stars, many accompanied by their own retinues of planets. While these systems often appear isolated, they are far from solitary. Instead, they live within dynamic galactic neighborhoods, where stars occasionally pass close enough to influence one another's destinies. Stellar fly-by near passes of stars by one another are not just rare cosmic curiosities. They are an integral part of the ongoing evolution of planetary systems. These encounters can trigger dramatic changes, destabilizing orbits, ejecting planets, or even exchanging celestial bodies between systems in dense regions such as stellar clusters or the galactic core. Close encounters are more frequent. Stars move in complex orbits around the galaxy's center, and gravitational interactions become a constant source of dynamism and change. Here, planetary systems are buffeted by neighbors, making stability a luxury, even in more sparsely populated regions like the Sun's neighborhood. Stellar encounters still occur on timescales of millions of years. Proxima Centauri's upcoming passage near our solar system is a perfect example, relatively close approach with potential to perturb distant objects and influence the architecture of our system. Such interactions have profound implications for planet formation and survival. Close stellar flybys can truncate protoplanetary disks, limiting planet formation or altering the composition and placement of emerging planets. They can eject planets into interstellar space, contributing to the population of rogue planets wandering the galaxy. They can trigger comet showers that bombard inner planets, influencing the course of biological evolution by causing extinctions or delivering vital organic compounds. Moreover, the frequency and nature of stellar encounters shape the diversity of planetary systems observed by astronomers. Systems that endure few perturbations may develop orderly arrangements like our own, while those subjected to repeated flybys display chaotic orbits, hot Jupiters, or planets in highly eccentric paths. From a cosmic perspective, planetary systems are not isolated islands, but members of a vast, interconnected community, influenced by their neighbors and the broader galactic environment. This connectivity adds layers of complexity to our understanding of habitability, planetary longevity, and the potential for life. Our solar system's relative tranquility may be a fortunate accident of location and timinga, temporary respite in a galaxy of dynamic interactions. But it is a reminder that stability is fragile and impermanent, always subject to the gravitational whims of passing stars. In the next chapter, we will explore how understanding these galactic dynamics helps us predict the future of our own solar system and guides the search for life beyond. Chapter 19: Predicting Our Future. Lessons from Galactic Dynamics. Understanding the complex dance of stars and planets within our galaxy offers profound insights not only into the history of our solar system, but also its possible futures. By studying galactic dynamics, astronomers piece together how stellar flybys, gravitational interactions, and cosmic environment shape planetary systems, including our own. One key lesson is that the solar system's long-term stability is never guaranteed. While it has endured for billions of years, it exists within a dynamic and sometimes hostile neighborhood. Passing stars like Proxima Centauri remind us that gravitational nudges, however subtle, can cascade into major orbital shifts over millions of years. Predictive models simulate scenarios where such interactions perturb planetary orbits, comet showers, or destabilize asteroid belts. These models provide estimates of impact probabilities, orbital resonances, breakdown, and even potential planet ejecti ends. Importantly, understanding these processes guides planetary defense strategies. By anticipating increased risks from destabilized bodies, humanity can better prepare detection and mitigation technologies, turning scientific insight into practical security. Galactic dynamics also illuminate the search for life beyond Earth. If close stellar encounters are common, then many planetary systems may experience periodic upheavals that challenge the emergence and persistence of life. Conversely, systems in more stable regions might offer safer havens for life to develop over long spans. This awareness sharpens the selection criteria for exoplanetary systems targeted by telescopes and probes, favoring those with stable orbits, fewer nearby stars, and minimal dynamical disturbance. Moreover, the possibility of interstellar material exchange during stellar flybys opens new pathways for panspermia, the hypothesis that life can spread between star systems. Cosmic dust, comets, or even captured planets might ferry organic compounds or microorganisms, seeding life across the galaxy as we project forward. The question of our solar system's future becomes intertwined with galactic motions over the next few billion years, encounters with other stars, passage through dense molecular clouds, and the evolving Milky Way spiral arms will continue to shape our neighborhood. These grand-scale processes set the stage for the ultimate fate of our planetary family, whether it remains a stable cradle for life, experiences upheavals and rebirth, or disperses into the galaxy as planets wander the stars. In embracing these cosmic rhythms, humanity gains not only foresight but perspective. Our home is part of a vast, ever-changing universe where change is the only constant dot in the final chapter. We will reflect on the profound implications of Jupiter's fate and our place in this dynamic cosmic dance. Chapter 20, Epilogue: Reflections on Jupiter's fate and our cosmic journey. The story of Jupiter's possible fate, a collision, a capture, or a cosmic exiles, serves as a profound reminder of the impermanence that defines our universe. From the vast expanse of space to the delicate orbits of planets, everything is in motion, subject to forces both gentle and violent. Jupiter, once the mighty guardian of our solar system, may one day no longer hold that role. Yet its journey whether ending in fiery embrace with the Sun, a new orbit around Proxima Centauri, or a solitary voyage through the interstellar darkness of cosmic evolution, we, too, are travelers. Our existence, precarious and precious, is shaped by gravitational tides and stellar encounters beyond our control. Understanding these forces does not diminish our significance. Rather, it deepens our appreciation for the fragile miracle of life and stability as we gaze up at the night sky, pondering the fate of the gas giant. We are invited to see ourselves as part of the grand cosmic dance of creation, destruction, loss, and renewal. This knowledge empowers us to prepare, adapt, and perhaps one day journey beyond our home star. It challenges us to cultivate resilience, to innovate, and to cherish the fleeting moments of peace our solar system provides. Ultimately, Jupiter's fate is a mirror for our own, a call to embrace change, to seek understanding, and to boldly face the mysteries of the universe.